So we have already seen how to change a double integral from Cartesian coordinates to polar coordinates and a triple integral from Cartesian coordinates to either cylindrical coordinates or spherical coordinates. And we have seen that we have pretty much the same pattern. That is, we have to take care of the domain, express the domain using the new set of coordinates. Then we have to express the integrand in terms of the new coordinates. And finally, we need to multiply by the Jacobian, which is different in each context. So we would like now to describe the general process. And the general process goes as follows. Let's work it out for two variables and see what is going on. So imagine that you start with Cartesian coordinates. Actually, one could have started with any coordinates, but let's say for the sake of the argument that we have Cartesian coordinates and we have a domain D. And we use the change of variable. We express x and y in terms of two new variables as x of uv and y is y of uv. And this means that every point on the xy plane that belongs to D will correspond to some new point in or some point in the uv plane. And so we have the description of D in terms of u and v. And let's say that we have the integral of f of xy. And now allow me not to write dA, which is our usual way of writing a double integral, but instead use a more old-fashioned, but a little more revealing as far as the variables are concerned, notation dx dy. I mean, this is a possible notation. The reason we have avoided this notation is simply because we don't want to, we want to clearly distinguish between double integrals and double iterated integrals. Sometimes people think they're the same, but what we have done is to present how a double iterated integral is a means to compute a double integral, same thing for triple integrals. So here we emphasize that the integration is taking place with respect to x and y. And we would like to see how we can change this to u and v coordinates. And the idea is that we have to work over D, but expressed in u and v coordinates. So expressed. It's a different set. I mean, it would make sense to even use a different letter here. But let's use the same one. And then the second step would be to take the integrand and replace every occurrence of x with its equal in terms of u and v, same for y. So that will give you a function of u and v. And now let me write the differential here, du dv. And then eventually we need the correction factor, the distortion factor, which will be in absolute values. And it's what we call the Jacobian determinant, which has this very interesting symbol. So it's the partial symbol, and on the top and the bottom we put the, so this is the Jacobian determinant, or simply the Jacobian. And let me tell you what that is. And let's realize here that the Jacobian determinant would be positive or negative, but by putting it in absolute values, we always suppose that it's positive. So the Jacobian determinant for two variables, and its expression for any number of variables, I think will be obvious when we say how it's for two variables. It's the derivative of x with respect to u, the derivative of x with respect to v, the derivative of y with respect to u, and the derivative of y with respect to v. This is the Jacobian determinant. And before we get to any examples, let's note something very, very interesting. So let's write down the formula for substitution of one integral. We should, of an integral in one variable. let's first of all notice here that the change of variable is pretty much a generalization in any dimensions of the substitution formula for an integral of one variable. So when we have one variable, usually what we were doing is we would take this integral and let's make it a definite integral. And we would go to the integral from g of a to g of b of f of u du. That's the substitution formula. And that's the way we use it. That's the way that we learned it in Calc 1 or Calc 2. And that's the way we use it. But there's something very interesting. I mean, if you pay attention to the two formulas, because that's the way we're going to use the change of variable formula, you will realize that the analog of this in the above formula is exactly that. So in some sense, it's the same formula. It's an equality. An equality is obviously symmetric. A is equal to b, b is equal to a, but we gave it in the way that we're going to use it. And here we expect to use it this way, whereas here we use it that way, which is pretty much the converse, because this is what the Jacobian would be like. Again, there is or the analog of the Jacobian. Now there would be a question about why we don't have it in absolute value. And actually, let's quickly answer that question. It's because the absolute value is not needed since we take g of a from g of a to g of b. So if that derivative happened to be negative, then the function would be decreasing. So you would get the integral in the, how should I put it, the wrong order. So by putting it in the correct order, it would be as if you multiplied the derivative by -1, thus getting a positive function. So it's in some sense, the two formulas are the same, even though it seems that one is missing the absolute value that the other has. The question that, of course, begs to be answered is why we are using them in opposite directions in each context. And the answer is very simple. In the case of integrals of one variable, our goal was to pretty much simplify the integrand. The domain was irrelevant in that case. The domain is an interval. You change it to, you substitute a new variable, the domain is still going to be an interval. But in the case of several variables, what we really target is the domain. I mean, we're not completely oblivious to what the integrand is. We don't want to get an integrand that is impossible to work with. But in most cases, what we're trying to do is get a much more convenient domain than the one we started with. And hence the difference in how these formulas are usually treated. Okay, let's jump to an example because we have said enough without having done an example. Why don't we actually start with an example in 3 variables? So as an example, consider this. Find the volume of the ellipsoid x squared over a squared plus y squared over b squared plus z squared over c squared is less than or equal to 1. Okay, so here's the solution. So the solution is that we are going to use the following change of variables. So x will be AU, y will be BV, and z is going to be CW. Obviously, UV and W are the new variables. Let's write z a little better because nobody can say it this way. And the Jacobian is very simple, right? No, before actually we go to the Jacobian, let's see what happens to this domain. The way to understand what happens to this domain is simply by replacing x, y, and z by their equals. It's not always going to be the same thing, but when you have such an inequality that defines your domain, then you will be able to figure out what happens, how to describe the new domain by just working with the inequality in the new variable. So here we will have au squared over a squared plus b v squared over b squared plus cw squared over c squared is less than or equal to 1. So you will have u squared plus, after the simplifications, u squared plus v squared plus w squared is less than or equal to 1. So our ellipsoid in uv coordinates, uvw coordinates, is simply the unit ball. Okay, so time to do our computation. So we want the volume. Let's call this ellipsoid U. That would be the triple integral in Cartesian coordinates of the function 1. Let's call it U, I'm sorry, not D. So we would have now to consider U in UV W space, that's the unit ball. And the function remains 1. I'm sorry, not dA, dV. It's a triple integral. And the question is, what is the Jacobian? So the Jacobian, which can be computed pretty easily, will be. So I want the partial. Let's actually write it once so that we don't forget what. It's a very nice expression. It has some fine symmetry to it. And the partial of x with respect to u, that's a, and the other two partials are 0 because there is no explicit occurrence of v or w in the expression of x. It's right here. Then the other one similarly will be 0, b0, and the last one will be 0, 0, c, which means that the whole thing is abc. Here we assume that a, b, and c are positive numbers. So we're going to put this, and this is going to be dv. Again, here I could have used dx, dy, dz. I'm having a triple integral here, and here du, dv, dw. But the bottom line is that you're actually, in both cases, you're integrating a constant function. So we can pull out abc, and what we're left with is the volume of the unit ball. And of course, we know what the volume of the unit ball is. We have found the expression 4 pi r cubed over 3. So if r is equal to 1, then we're going to have abc times 4 pi over 3. So we get eventually the volume of the ellipsoid is 4 pi over 3 abc. If you think about it, this is a direct generalization of the volume of the sphere. If you have a sphere, if and only if the ABCs are equal to each other and they're equal to the radius of the sphere, so you recover right away the formula 4 pi r cubed over 3. So this is a direct generalization of that formula. Okay, so now let's do another example in 2 variables, but a far more interesting example. An example where now we will use a change of variable that is not at all obvious. So let's present the domain first, the initial domain. So let D be the domain so here it is. So I'm taking the bisector, first line, so this is y equals x. Then I'm taking the one that has slope 2, so this is y equals 2x. Then I'm taking the line x plus y is equal to 1, And finally, I'm taking the line x plus y is equal to 3. I'm afraid that my proportions here are quite off, but I don't think it should be a big problem. So here's what we get. It's a quadrilateral. It's a trapezoid, actually, to be more precise. It's a trapezoid. And if we wanted to compute the integral here directly, we would have to pretty much break it in 3 parts because we would need to have the same formula for upper and lower boundaries. So these are the 3 parts that we would need to split. But we're going to do the following. So we're going to say apply the change of variable. We give the change of variable here. And in most cases, you will be given the change of variable in such an elementary setup because otherwise it's almost impossible to figure it out yourselves, for example, in a case like this. So the change of variable here is a very strange one. It's x is equal to u over v plus 1, y is uv over v plus 1. And to compute the double integral over d of x plus y dA. Okay, so this is the double integral that we would like to compute. So let's get to work. The first thing that we need to do is figure out what the domain becomes in terms of variables u and v. And it better be a good one. It better be a good one. So how can we figure this out? Well, we have the equations of the boundary lines. So the idea is pretty simple. Let's find what those equations are in UV space, what they become in UV space, and that should give us the boundary lines of the new domain in UV space. So let's see. So let's start with y equals to x, right? So replace y by uv over v plus 1 and replace x by u over v plus 1. So this cancels with this cancels with that, and v is equal to 2. So that's the first line. Okay. What is the second one? So take y equals x. That should be even simpler. So you have uv over v plus 1 is equal to u over v plus 1. This cancels with that cancels with that. I mean, you have to here make some assumption about u not being equal to 0, which I think it's going to be pretty straightforward given that x and y are both positive over this domain. So it's easy to see that u and v are going to also be positive. And this will give you just v equals 1. And then take x plus y is equal to 1. So this will give you u over v plus 1 plus uv over v plus 1 is equal to 1. And here's something very, very nice happens. So you can take the two fractions have the same denominator, and in the numerator you can factor out u, and then you get v plus 1 or 1 plus v is the same thing. And these two things cancel, and that is equal to 1. So you get u is equal to 1. That's our other line. And finally, we have x plus y equals 3, and u over v plus 1 plus uv over v plus 1 is equal to 3, which gives us u times v plus 1 over v plus 1 is equal to 3, which means u is equal to 3. So these are your 3 lines. And now if you draw this domain in UV space, oh, it's so nice. So this is your UV space. V equals 1 and v equals 2, these are 2 horizontal lines. And u equals 1 and u equals 3 are 2 vertical lines. So this is u equals 1, u equals 3, v equals 1, and v equals 2. And this is your domain. So the new domain is simply 1, 2, 3 cross 1, 2. Splendid. Let's go to the integrand. The integrand is x plus y, and I think we have already seen the trick. So this will be u over v plus 1 plus uv over v plus 1. So this will be u times v plus 1 over v plus 1. Simplifications. And the integrand becomes u. The integrand is very, very simple. And finally, let's work out the Jacobian. Okay, so what is the Jacobian? So the Jacobian, let's write here the expression so that we don't forget them. So it's u over v plus 1. Y is uv over v plus 1. So this is the derivative of x with respect to u is 1 over v plus 1. The derivative with respect to v is minus u over v plus 1 squared. U is treated as a constant here, so that should be pretty straightforward. The derivative of y with respect to u is v over v plus 1, and the derivative of y with respect to v, well, that might need a little work here, so it's going to be u times v plus 1 minus quotient rule minus uv times 1 over v plus 1 squared, which is the same thing as uv minus uv cancel each other, and you get u over v plus 1 squared. So I put this here, u over v plus 1 squared, and let's see what we get. So you multiply the entries in the main diagonal, and that gives you u over v plus 1 cubed minus, and then you have an extra minus, so that becomes plus uv over v plus 1 cubed. And here it's again the same trick, right? So you have the same denominator, which is v plus 1 to the third power. You factor out u, and what stays in is 1 plus v. V plus 1 is the same thing, which cancels with this and gives you u over v plus 1 squared. That's your integrand. And now you have everything that you need. Let's put everything together now. So what did we say? U was from 1 to 3, du, and v was from 1 to 2, right? That was the domain that takes care of the domain, step 1. Then our function, our integrand was simply u, and our Jacobian is u over v plus 1 squared. Guess what? This integral splits. What do we mean by that? That we can write it as a product of two integrals, one in u, one in v, because the endpoints are constant, and the integrand is a product of two quantities, one that contains just u and one that contains just v. So this will be equal to the integral from 1 to 3 of u squared du times the integral from 1 to 2 of dv over v plus 1 squared. And this will be u cubed over 3 from 1 to 3. So this will be 27 minus 126 over 3. And this will be from 1 to 2, the antiderivative of 1 over v squared, v plus 1 squared is negative 1 over v plus 1 from 1 to 2, which is pretty much, if you do the simple math here, it will be 1/2 minus 1/3, which is 1/6. So if you multiply the two things together, you will get 26 over 18, same thing as 13 over 9. And that's it. Okay, this is obviously a much more interesting example. And it would be a good idea to actually go back, pause the video, try to do the two examples yourselves carefully, and see all the steps, the 3 steps, as they're being performed for each of these integrals. And that's it. Thanks for watching.